Let's look at how we can utilize a GIS model to find the optimal locations in which to place a 5G telecommunications tower. 5G, of course, meaning the 5th generation of cell phone technology. For more information, you can have a look at a paper that I did in 2006 that did this for 4G technology. So suppose I want to find where it would be profitable to locate a cell phone tower. So that's very important for businesses like TELUS, Bell, Rogers, etc., who run cell phone networks. So it costs money to put a tower up, and that cost must be recouped before profitability can happen. So the business analysts have found, based on what they do on looking at costs and return times, return on investment times, and profit, that we would need to have 3,000 people within 1 kilometer of the 5G tower in order to make it profitable at an accepted time in the future. So looking at this, we need something with people. So we need to have a raster that represents, for each cell, how many people are in each cell. And then we have to look within 1 kilometer of each cell at the sum of the people and see if it exceeds or meets 3,000. If that cell does meet or exceed 3,000 people, then we know it is a potential location for a telecommunications tower. So we need population, a raster population, and then we need to be able to look at each cell individually and all the cells within 1 kilometer of that cell that we're looking at. And that's using what's called a focal function. We'll have a whole lecture on focal functions later on in the course. For now, all you need to understand is that the focal function for each cell looks within a distance of each cell and computes statistics that we might want. For example, one of those statistics, even though it's not really a statistic, is the sum. So with population into a focal sum, we can get population within 1 kilometer as the output raster. Once we have the population within 1 kilometer for each cell, then we just have to look at which ones are greater than or equal to 3,000 people. So that goes into the second process here. Greater than or equal to 3,000 is looked at for each cell. Each cell that meets this condition is considered true and gets a value of 1, and all other cells will get a value of 0. And the output then is a layer with potential tower locations. So at that point, we could look at properties for sale, or who's on each properties, etc., to find out how we could go about putting the tower in place. So the first process in a cartographic model in this case is just two processes together. The first one, which we just saw, is the population focal sum, gives pop within 1 kilometer for each cell. So the output raster for every cell tells us how many people there are within 1 kilometer of that cell. That is then the input to the second process, which is a simple relational operation. We'll say that's greater than or equal to 3,000. And the output is basically just like our suitability model. It's a suitable locations for a tower in this case. So the concepts aren't any different. It's just a different example. Now in this example that we'll be doing in ArcGIS Pro, it's in the region of Ottawa. And so we will have to match all of our, or set all our critical environments to the population layer. And so this is a thing to remember, that once we switch in ArcGIS Pro to a new region of analysis, we have to reset our environment settings to some control layer, which will be called, in this case, population, which is in the module 3.4 folder. For Python, if it's our first time, if you've just opened ArcGIS Pro, you'll have to do your imports. So those are the standard import ports I've mentioned a number of times already. And then we'll make a raster variable using the raster function and the population raster layer. Then we reset all the environments in Python. So that will remove any previously set environment settings in the Python window. At that point, if we've already set application level environments for the population layer, which we will have already done in this case because we'll create the cartographic model first, we don't have to go any further. We don't have to do this stuff because all these settings will be taken from the application level. We only have to do this when we want different things than what's at the application level environments. But this is important to make sure we get the application level environment passed down as it is, just changed previously. So in terms of the cartographic model, it would look like this. Population, focal statistics sum, pop within 1 kilometer, and then a greater than, 3,000, and tower location. Tower lock is the output. The Python script equivalent would look like this. Popras, so that just contains population. If you'd created it already on the previous slide, that would be fine. And then we have to do one more thing here. To use focal statistics, we have to define a neighborhood that will be used around each cell. In our case, we're looking at a radius, so a neighborhood that's made of a circle. So it's called NBR circle. And then we put the units. 1 kilometer would be 1,000 meters because maps that are projected are usually going to have linear units of meters. And we have to specify that's 1,000 map units. And this is then called a neighborhood object in this case. Then we say sum pop, which would be the sum of the population around each cell, would be equal to focal statistics. The input would be the popras variable, and then the neighborhood is next. And we want to do a sum in there. Then, once we have sum pop, we simply say, okay, sum pop greater than or equal to 3,000. And we assign that to the tower lock, like that. And then we have, again, we'll have the same results in both methods. The first thing we need to do in order to find the optimal locations for a 5G tower is to go and add in the data we'll need to ArcGIS Pro, I should say. So I'll go to my data folder again, which is from the module 3, and I'm going to bring in population. And I'll just drop it in there. Here we can see what is called the population grid. And a lot of it looks very dark. Each cell contains how many people there are within that cell. So in that case where I click, there's likely nobody there, 0.000983 people. Here in the town of Richmond, if I just zoom in a bit, well, I can start to see where there's more people. If I click in a white area, for example, it's a higher value, and there's a half a person in that cell. So in reality, of course, there's not half people, there's not quarter people, there's not 0.0009 people. But in order to represent the number of people within each of these homogeneous regions, we have to assign the population and break it up into how many people would be in each cell in total. And that's what this particular raster layer represents. So I'll go back out here. You could re-symbolize it if you want. to see a slightly different contrast, I can click on my Appearance tab, Symbology, Stretch, and I could use a multicolored one if it would make it easier to see the different things, like so. Although it is a continuous data, so I would want something which is a single color scale in any case. So chain the single hue scale, for example. So all reds or all greens or all blues. Look at this one here. So here we have the hue is red and the value of that changes. The value is from nothing, no red, to 100% red over here. And the maximum number of persons in a given cell that's found is given by the maximum here in the population layer, and it says 0.722929 persons in that cell. So there could be a few cells with that number. So now I'm going to go over back to my catalog view. I'm going to go to our toolbox that we've been working in, or I can create a new toolbox. Let's just create a new one again so we can have a reminder on how to do that. I want to make my toolbox here actually in the Ottawa geodatabase because that's where my data is. So I'll right click and say new toolbox. I'll call it G5 for 5G. Generally don't start the names of things with numbers in Microsoft Windows environments. So now on my G5 toolbox, I'll right click and I'll say new model. And that will open up the model window, and population is going to be my input. So I'll drag it in. I'll maybe zoom in a bit on that so we can see things more easily. So we have population. Then I'll click on geoprocessing and then toolboxes and go down to my spatial analyst toolbox. And in the spatial analyst tools, we will see a neighborhood toolbox, and I'll expand that. And in here we have our focal statistics, and that's what we want. So that will be the first thing. I'll drag it in. So I'll just move these over here to the beside population. Now, before I go any further, I want to make sure that I set my environment. So I'll go back to my analysis tab up top, environments, and I have to change everything to match population. So coordinate system, same as population. And notice here that it's set to my old thing, which is in Vermont. So it's a good thing that I'm setting them and resetting them now, population. Extent, same as population. Cell size, same as layer population. Mask, population, and snap raster population. And I'll click OK. If I hadn't have changed those, everything would have worked fine, except I'd have no output. And I'd be wondering, well, why is it running and there's no output? Well, it's because the processing extent is set to someplace in Vermont, and this is not in Vermont, so you don't see anything. So it's really important there to make sure that you set your environments. So that is the application level environments. So now I'm going to connect population to focal statistics as the input raster. But we have to double click on focal statistics to set the correct parameters. Neighborhood we want as a circle, and the radius to be 1,000 units, map units. So the map horizontal units, which are meters. And we also want the statistics type to be sum, not mean. So I choose sum. And I click OK. So that produces the focal statistics. And I'll just rename the output here as pop underscore WTHN, so pop within underscore 1 km, like so. Now, this is an intermediate piece of data. So I'm going to go over to my math tools, math, because I want to know which cells have a population greater than or equal to 3,000. So in math, I go to logical and I find greater than equal and I drag that in. I'll just move it up here. I'll connect the output of my first process, which now tells us how many people there are within 1 kilometer of each cell, to the greater than equal as input constant value 1. Then I'll double click on greater than equal to set the condition, which is 3,000, because I want each cell within the pop within 1 kilometer to be compared to the value 3,000 in such a way that the comparison is that cell containing greater than or equal to 3,000 people? And I'll click OK. And that produces that second input, which I'll quickly rename to 3,000 to remind me what that is in this comparison for the relational operation. And I'll also rename my output tower lock, because that's my final tower location. Like so. So population per cell has gone into a focal statistics with a circle radius of 1,000 meters. So every cell in population will have assigned to it the sum of all cells around that cell within 1,000 meters. And then we have an output raster where each cell contains the number of people within 1,000 meters of each cell. Then I use a greater than equal to say which of those cells is greater than or equal to 3,000 people. And then the final output here is the potential tower locations that could be profitable. So I'll click back I'll go back to my model builder tab and I'll click save, and then I'll run this after I validate it. So validate is good. Now I run. So the focal statistics can take a little bit of time because it's computationally intensive. So it's generally one of the slower operations. The greater than equal is very fast comparatively. Now we see the drop shadows, meaning that this is this model is in a already run state. So I'll right click on tower lock and say add to display, and then we can have a look at it right there. That small region, within that small region, is where we could potentially locate a tower, and anywhere in there would be enough people within 1 kilometer to make this profitable. So there would be 3,000 or more people. We could have done that as well in map algebra. So I'll open the Python window. This is my first session, so I'll do my imports. I'll say from arcpy.sa import all. I'm not going to bother with environments because I've set them globally, so I'll just let the Python window inherit the global application level environment settings. But I will do this in case there are any other environment settings in the Python window. There shouldn't be, but we can check, for example, I can say from arcpy import env. I can say env.snapraster population. So because it was the first time, my first Python session of the day, and I took my environments and set them up here in the global or application level, all of the critical environment settings are already set to population. So I could say env.cell size. And again, it shows me the population raster. So that being said, now we will first do a focal statistics. And to do that, we have to create a neighborhood object. So I'll say NBR equals NBR circle right there. And then the radius, 1000, comma, the units, or cell or map. And when we look at this in more detail, we won't be using map units. We'll always use cell units, but for now, we're just going to use map units for this example. And that's it. Hit enter. Nothing happens because this is now just a neighborhood variable called NBR, which can be used in the focal statistics. So for the focal statistics layer, I will call it pSum for population sum equals focal statistics. The input raster, I should have made a raster variable for the input raster, but I didn't, so I'll just choose population right here because it's in my table of contents. The neighborhood, NBR. The statistics type, we want sum. And we want data so that no data is ignored in the computations. And that's all we need. And now we hit enter. And that will create a focal statistics sum called pSum. And you'll even see what it looks like. So I'm just going to move or close my Python window for a second so you can see what the pSum looks like. In fact, in terms of the number of people around any given cell, it ranges from 0 people, I'm looking here in the contents, to 3,428. And that's probably somewhere in here. If I click anywhere in here, for example, I can see that most of those are over 300 or 3,000 people. 3,200, 3,266, etc. Going back to my Python window, the last step is to create tower lock, and I'll call it tower lock 2. And that's equal to the pSum greater than or equal to 3,000, like so. And that will create an identical output as did our previous cartographic model. Turn off pSum here, and I can turn them on and off. You can see they look identical, just different colors because it's randomly assigned. Just to prove that they're identical, and there are no differences, I'll do my standard thing, which is a difference map called D equals raster tower lock, raster tower lock minus tower lock 2. Like so. And D, that raster should be 0 for all the cells. And indeed it is. So everything worked the way we'd expected it to. So now that region, that small region, and I'll just make 0 no color, for example, here. So this small region right there is potential areas, or a potential area in which a tower could be located. So then the site location people would go and start looking at that particular region to find out, what buildings are there, ownership of parcels, availability of parcels, any types of things like that they need to figure out to put a tower up on properties that exist. Let's make that partly transparent, not 100% like that. And I can even look at the map underneath it, so I can turn off the population and see that, okay, well, these are the types of things in there. You look at the buildings and whatnot that are on the base map. Looks like a large area here where maybe something could go, etc. And then that's other work to be done in the by somebody else, or perhaps by the analyst as well.